This video will cover section 6.4, vectors and dot products. The objectives for this section are to find the dot product of two vectors and use the properties of the dot product. Also to find the angle between two vectors and determine whether two vectors are orthogonal. Write a vector as the sum of two vector components, and the last one, use vectors to find the work done by a force. So we will look at force as a vector, and just so you know, we will go over the definition of orthogonal vectors, but just so you get an idea, they will be two vectors that for which the angle in between them is 90-degree angle. Is a 90-degree angle or a right angle. So the first objective is the dot product of two vectors. In this section, we will study a third vector operation. Remember, on the previous one, we did addition, subtraction, which is one operation, and then we went over scalar multiplication. So now the dot product is the next one, and with this operation, the result is going to be one number only. And not a vector. So it's going to be a scalar. So if we have two vectors, as you can see here, vector u and vector v, the dot product between those two is going to be the product of the horizontal components first, as you can see here, and then we're going to add the product of the vertical components, as you can see here. So that's why if we have the result of two numbers being multiplied, it's gonna, from the horizontal components, it's gonna give us a number or a scalar. And here, the product of the vertical components will also give us a scalar. So if you add two numbers, you will also get a number, or a scalar plus another scalar will give us another scalar, or a constant, or a real number. So the result of a dot product is not a vector. Not a vector. That is very important. So we do have some properties for the dot product, and here we're going to consider the vectors u, v, and w to be vectors in the plane or in space, and c, the letter c, is going to represent a scalar or a real number. So the dot product, it is commutative, meaning that if you change the order of the vectors, you will get the same result. So in this case, the vector u dotted with v is the same as v dotted with u. Next, number 2, we have the dot product of the zero vector with any vector is always the number 0, not the zero vector. The one that is bolded is a vector. The one that is not, that is just a number, the scalar. The number 0. The third property is the associative property. So if you have a vector dotted with the addition of two vectors, you could perform the addition first of the two vectors and then perform the dot product. In this case, you will distribute it so that you perform the dot product, or the other way to do it will be to distribute by performing the dot products first and then at the end adding those two constants. But in both ways, the result will be a number. Fourth property indicates that a dot product of a vector with itself is equal to the magnitude square. And you, of course, recall that to find the magnitude, for that, we take the square root of the square of the horizontal components plus the square of the vertical components. So similar to the distance formula or the Pythagorean theorem. So if we were to square that, then we will just be talking about that without the square root. So if we square that, then we do lose the square root. So that is what we have here for property 4. Number 5, we have a scalar, that's c, and we have the dot product of vectors u and v. So in this case, you could do the dot product first, and then at the end distribute the scalar. That is the first option that we have here. Or you could distribute the scalar to one of the vectors and then do the dot product. So in this case, you distribute it to vector u. But you could also choose to distribute the scalar to vector v and then do the dot product with vectors u and cv. In this case, we're not distributing the scalar to each vector, because if you do that, it will be wrong, like saying something like this. This will be wrong because that will be something like distributing c square. And as you can see here, we're not doing that. The scalar is just simply c. So don't do that. Don't distribute it to both, just to one of them, either to the first vector or to the second vector. Or you could just do the dot product first. From here, you will get a scalar, a number, and then you just multiply a number times another number. Let's call it k, just to generalize it. Okay, so we're going to practice how to do the dot product. It's very, very simple. You just have to be careful with your signs. So we're going to get the two horizontal components, so 4 times 2, and then plus 5 times 3. So 4 times 2 is 8 plus 15, and that will equal to 23. For the next one, we're going to have the product of the horizontal components, 2 times 1, plus the product of the vertical components. Notice how here we have a -1, so I'm going to keep that in parentheses just so I don't forget to distribute the negative. So 2 times 1 is 2, and here -1 times 2 is -2, so 2 minus 2 is equal to 0. And this is actually very important. Remember that word from the beginning, orthogonal vectors. And so the angle in between them is 90, but also the dot product is equal to 0. So we could say that these two vectors are orthogonal. And we're going to go back to that definition in the next slides. So the next dot product, we multiply 0 times 4 because those are the horizontal components. And then we add the product of the vertical components, which will be 3 times -2. So this is going to equal to 0 minus 6, which is equal to -6. Remember, the solution or the answer for a dot product is always one number and one number only. It's not going to be a vector or two numbers. Okay, so the next thing we're going to do is find the angle between two vectors, and in this case you could consider our vectors to be u and also v. And so the angle we're looking for is the one that is formed between them, and that is, we're going to refer to it as theta. Now that angle is going to be, it could be 0, as you can see here. So it's going to be greater or equal to 0. So that means 0 is included. Or in n, it will be less than or equal to pi. So in degrees, theta will be greater or equal to 0 degrees or less than or equal to 180 degrees. Between their respective standard position vectors, as you can see on the figure here, 6.26. And the angle, it could be found using the dot product. So to find the angle, we're going to use the dot product for the numerator of this expression. And we are going to use cosine of theta, but at the end, since we do have to solve for theta, you know that we will be taking the cosine inverse of the dot product of vectors u dotted with v divided by the magnitude of vector u times the magnitude of vector v. And of course, we will be entering all of this on the calculator. But while we do that, we are going to have to enclose, of course, certain things. Or we could find the dot product first and then find the magnitude. So there's several ways to approach the problem. And remember, to find the magnitude of a vector, we will be using the square root of the square of the horizontal component plus the square of the vertical component. And then, of course, to find the magnitude of the other vector, we will look at its own components. So it will be the square of v sub 1 squared, that's the horizontal, and then plus v sub 2 squared, so that will be the vertical component. So we have two vectors here, vector u and vector v. And we are going to find the angle that is in between them, for example 3. So first of all, let's go ahead and divide our slide like this. So first we need to find the dot product of uv. So remember, we're going to multiply the horizontal components first, 4 times 3. And then we're going to add 3 times 5. So we will get 12 plus 15, and that will equal to 27. So we're going to save this, and that is what we're going to substitute here for the dot product. Now let's go ahead and find the magnitude of u, of vector u. So we have that vector here, and so we need to take the horizontal component and square it, so that will be 4 squared plus the vertical component square, so that will be a 3 squared, and that will give us the square root of 16 plus 9, which is equal to the square root of 25, and that is equal to 5. So for the magnitude of vector u, that will be equal to 5. And now let's go ahead and find the magnitude of the other vector. So for that, we're going to have magnitude of vector v. So we take the horizontal component, which is 3, and then we're going to square it. So 3 squared plus the vertical component, and then we square it, so 5 square. So from here, we're going to have the square root of 9 plus 25, and that will give me the square root of 34. And that result is what we're going to replace magnitude of vector v with. So now let's go ahead and do our substitution. So for the dot product, we got 27. The dot product between vectors u and v. Then on the denominator, we're going to need the magnitude of vector u, which is a 5, times the magnitude of vector v, which is the square root of 34. And the square root of 34, we just leave it inside the radical because we don't want to get a decimal and then round too soon, because we still need to find the angle theta. And so you could see the answer is here, 27 over 5 times the square root of 34. But remember, now we need to find what theta is. That's what we're looking for, not the cosine of theta, but the value of theta, because we want to know the angle measurement for the angle in between those two vectors. So as we discussed previously, we're going to take the cosine inverse. And you can see here cosine inverse of that quantity that we obtained previously. So if we enter all of this on our calculator at once, and we don't really need to rationalize the denominator, so let's see. So I'm going to clear my screen, then cosine inverse here, and I forgot what is it, 27 divided by 5 times the square root of 34. 5 times the square root of 34, and I'm going to go ahead and close the parentheses. And as you can see on my screen, the calculator is set in degrees. And so let's actually see what we got in degrees. Okay, and so I got an error. I'm not sure why. So let's go back and try to calculate this in radians. I don't know if that is the problem. Maybe I entered wrong. So we go to mode, radians. Oh, go back to the main screen. And I'm going to, without typing it again, I'm going to use my up arrow to highlight it. And once you can see it's highlighted on your calculator screen, the expression that we used previously, press enter, and that does something similar to copy paste. So you can see it now. I'm going to press enter, see if I can get it, and it keeps saying error. I'm going to pause the video and figure out what's going on. So I found the problem, and what I did, I just included an extra set of parentheses around the denominator of the expression. So around the 5 times square root of 34. And also I just entered the multiplication symbol, but I don't think that is a big deal. So that is the answer in radians. I'm going to go ahead and see if we can find it in degrees. So we go here, switch the mode to degrees, and then go back to the main screen. So I'm going to enter now again, and so I'm going to enter 27 for the numerator. First of all, cosine inverse, then divide it, and then in parentheses, just to make sure that my denominator is together. And I'm going to skip the multiplication sign, see if it still works. So close parentheses to close the denominator, then close again to close the first parentheses right after cosine inverse. And we press enter, and that is in degrees, so it does work. And in degrees, it will be 22.17 if we were to round 2 digits after the decimal. So let's say 22.17. In degrees, and here is the answer in radians. And so what we did on the calculator, just so you're sure, we used extra parentheses here around the 5 times square root of 34, because without it, we got error messages. Okay, so from the previous formula that we just used, the cosine theta is equal to the dot product between uv divided by the magnitude of u times the magnitude of v. From there, we could derive the next formula if we just simply think of the product of the magnitudes dividing on the right side. If we take that across, so then it will be multiplying, so it will be here magnitude of magnitude of u times the magnitude of v, and then times here the cosine of theta, and that is equal to the dot product that we see here. And so what you see there is the same thing that we see here. It's just we have the left and right, so they're kind of like reflected about the equal across the equal sign. So that is what we called an alternative form of dot product. So the very first form of dot product that we started the class with was we take the horizontal component, so u sub 1 times v sub 1, those are the horizontal, the product of those two, and then we add the product of the vertical component, so u sub 2, v sub 2. So that was the first, from the, I don't know, second, third slide, the very first form of dot product that we went over. And then the other one will be the one that you guys can see here. When will that be more convenient? Well, if we know what the angle is and perhaps the magnitudes, that would be more convenient or easier to use than this form. But with that, we're also gonna do other things. So that alternative form of the dot product produces that alternative way to calculate it. From this form, you can see that because the magnitude of u and magnitude of v are always positive, the dot product of u dotted with v and cosine theta will always have the same sign. So here are 5 possible orientations of vectors depending on their direction. So we could have 2 vectors. Here we have vector vector v and vector u, and they are going in the complete opposite direction from one another, and you could see that the angle in between them is a straight angle, or 180 degrees, or equivalent to pi. So if you think about that, the cosine of pi with respect to that unit circle that we should all know, the coordinates of that unit circle will be -1, 0. And because we're talking about the unit circle, then we could assume right away that the cosine value is going to come from the x coordinate of that point of intersection, and that is for 180 degrees or pi radians. So the cosine is -1. Then if we have, let's go over the third one actually. If we have the angle equaling exactly 90 degrees, then we know that the cosine for 90 degrees, or for pi over 2, we will look at the coordinate, x coordinate on the unit circle, which will be 1, not 1, but 0, comma 1. And of course, you could see that the 0 is here. So the cosine of that angle will be 0. And that is a 90-degree angle, or pi over 2. Of course, we could have some in between. If we look at the area here of the first quadrant, we could have angles that are greater than 0, but also less than pi over 2, or greater than 0 but less than 90 degrees. So those acute angles, that's what we call them, and they're located in quadrant 1 with respect to the Cartesian plane. So right there, the cosine is gonna be between 0 and 1. And again, if the angle was to be 0, which in this case is not included because we don't have the equal part of the greater than or less than equal symbols, so the cosine there will be a 1. And so you could see that the cosine will go from 0, because we write the small number first, from 0 to 1, if the angle is acute. Now, if the angle is obtuse, as we can see here, and those will be angles that are, the terminal side is located in the second quadrant. So if we had an angle that starts here, of course, because it's in standard position, and we go this way, then the terminal side, if it's obtuse, is because it's greater than 90 or greater than pi over 2. So it makes sense that greater than pi over 2, but it's less than pi. So those will be, the terminal side will be in quadrant 2. So for that, if we look at the cosine values that we have here, 0 and -1. So remember, we start with a small one. So the cosine of theta will go from -1, will be greater than -1, or less than 0. Remember, we start from small to large, left to right, so -1 is smaller than 0. And then finally, we have here two vectors that are going in the same direction. One of those is vector v, right here, and the other one is the whole line, or vector u, which you could see how v is like embedded into u. They're overlapping. So in that case, if they are going in the same direction, the angle between them is 0 radians, or 0 degrees. That's the angle in between them, because they're following the same path. And you can see that by the arrows. So they have the same direction, and the cosine at 0 degrees or 0 radians is 1. The angle between two vectors, as we discussed that earlier, whenever the angle between two vectors is 90, the cosine of theta will be equal to 0. And if we were to use this form, the alternative form of the dot product, but we say the angle is 90, so the cosine is going to be equal to 0. So it doesn't really matter what the magnitude of u and V is for any number multiplying by 0 that comes from the cosine of theta will always give us 0. So if the dot product is 0, we could assume right away that the vectors are orthogonal. And that is what the definition says here. The vectors u and v are orthogonal if and only if the dot product of those two vectors is equal to 0. So the statement if and only if is a double-sided conditional statement. So it means that it is true if we say u and v are orthogonal. If u and v are orthogonal, then the dot product is 0. But also, if we read it in reverse, u and dotted with v is equal to 0. If that is the case, then the vectors are orthogonal. So double-sided if statement. Sometimes you might see in some books the abbreviation IFF, and that's what it means. If and only if. So it's a double condition as well. The terms orthogonal and perpendicular mean essentially the same thing, meeting at right angles, just like we saw the intersection or the angle in between them is equal to 90 degrees or pi over 2, and that is what we call a right angle. And so vectors that intersect like that, they're also called perpendicular, but also orthogonal. Note that the 0 vector is orthogonal to every vector u because the vector 0, remember, if it's bolded, is a vector. The 0 vector times any vector will always give you 0 because the components of the 0 vector are just 0 and 0. And so it doesn't matter what the components of vector u are. If we apply the steps to calculate the dot product, it will be 0 times u sub 1 plus 0 times u sub 2. And of course, we will have 0 plus 0, which is equal to 0. And so that's why we have that statement that says that the 0 vector is orthogonal to any vector, to every vector. So to find the components of a vector, that is a very useful skill because it could help you not only in this class, but definitely in physics and perhaps other engineering courses that you take. So you have already seen applications in which two vectors are added to produce a resultant vector. And so I know I didn't include a problem like this on the lecture, but there are a couple on the homework. And if you were to add two vectors and we were using something that we refer to as the parallelogram rule. So if we're adding, let's say, what do I want to do? Let's say this vector plus another vector. So if we do that, we could use, let's see, like a projection of this vector here, the longest. And I could kind of like position that vector here. And the original is here. So I could take the initial point of that vector, the one in purple, and place it at the terminal side of my first vector, the one in black, and then create that. And so this is what we call the parallelogram rule. And so the result of adding those two vectors will be here. The one that starts at the origin, at the initial points of both vectors, and ends at the terminal side of the second vector, the one that I projected. So that is if I was to add, let's say this is force 1 and this is force 2. And if we want to find this thing called the resultant force, it will be the addition of F sub 1, the first vector or the first force, plus the second force or the second vector. And so that is a very common question. You will have it in your homework for section 6.3. But now what we're going to do is do another type of application, but I just wanted to point that out. So I'm actually going to erase this one. Oh, well, let's just leave it here. This could be something useful for your notes. That will be the resultant force. Okay, so going back to the slide here, many applications in physics and engineering pose the reverse problem, decomposing a given vector into the sum of two vector components. Consider a boat on an inclined ramp, as you could see in figure 6.28. So we have the inclined ramp, we have the boat, and it says here the force F due to gravity pulls the boat down the ramp. So here is gravity, and it is perpendicular with the horizontal line. But here the ramp is inclined, so there is certain angles that we're going to have to find. And so I'm going to go back. The force F due to gravity pulls the boat down the ramp and against the ramp. So it's pulling the boat down, but also against the ramp. Sorry about that. So the vector that you could see here, W sub 2, that is the one that is pulling the boat against the ramp. So you could see it is making a 90-degree angle with the ramp. So if here's the ramp and here's our 90-degree angle with vector W sub 2. So that is the one against the ramp, W sub 2. So these two orthogonal forces, W sub 1 and W sub 2, are vector components of F, and W sub 1, as you can see, it's right here. So if we were to use the idea of the parallelogram rule, and we have, I'm just going to draw them here, W sub 1 here, and then, I'm sorry, that's not correct. I have a lot of stuff written here. So again, I'm going to color them. This is the one for F here. This is the one pulling against the boat, W sub 2. And then we have here W sub 1, the one that is on the ramp. And that one, depending on, I'm not a physics expert, but I would probably consider W sub 1 to be something like friction from the ramp. And then if we combine those two, in this case, W sub 1 plus W sub 2, we obtain F. So F is the resultant force here. But remember, in the previous section, we added two vectors to find the resultant force. Now we're going to do kind of like the opposite and break it down into two vectors. So right here we have the addition, like I was telling you, and that is what gives you F, the resultant force, which in this case we went over on the diagram, that was gravity. And we have here W sub 1 W sub 2. So the negative of component W sub 1 represents the force needed to keep the boat from rolling down the ramp, whereas for W sub 2 represents the force that the tires must withstand against the ramp. So that's a nice explanation. And remember, that's what's pulling the vector towards the ramp, so it doesn't fly away. And then W sub 1 is the force needed so that the boat doesn't roll down. And so, yeah, I guess friction could be one of those. So finding the vector components, and what we're going to do to find W sub 1 and W sub 2 is going to be something that involves projection, and we're going to do that by using the vector components. Finding vector components, we're going to go over the definition of vector components, and then I will do my best to explain the definition with the help of the of figure 6.29. Now the left side of the figure is one case and the right side is another case of orthogonal vectors. So remember that we're decomposing vector u, so it could be broken into two vectors that are adding each other. And also, we want to make sure that those two vectors, vector w1 and w sub 1, I should say, and w sub 2 are perpendicular. So essentially, we're looking at w sub 2 and w sub 1 like that. Or in the other example, this will be w sub 1, and we have here w sub 2. So you can see clearly that the angle there will be a 90-degree angle. So that is what we want. We want two vectors that are orthogonal. So it says here where w sub 1 and w sub 2 are orthogonal. Remember 90-degree intersection or angle between them, or also the dot product, and also the dot product will be 0. So another thing that will come from using this method and the formula is that w sub 1 is parallel to vector v. Now, this might be a little bit weird of what you're used to seeing as parallel. So when we talk about lines that are parallel, there are two lines like that will not intersect. So when we talk about vectors, parallel vectors are the ones that run in the same direction and that the intersection is a 0. So for example, I'm going to go back up, and that will be here. So we could say here that vectors u and v are parallel. And you could see that they are overlapping. Here's one of them, and then the other one is just a little, actually I'm gonna erase all this. So one of the vectors is vector u, the whole vector, and then vector v is a scalar multiple of it, or we could say vector v and then u is a scalar multiple of v, meaning we could have vector v here, and then u is gonna be the same as 2 times vector v. So going back to our current slide, it's actually here, our definition. So again, we have w sub 1 and w sub 2 are orthogonal, and w sub 1 is parallel or a scalar multiple of vector v. And actually what I want to do, I'm going to just change the colors of how I am highlighting here. And let's make this one W sub 2, W sub 2, and then the one that is gonna be parallel, it's W sub 1, but it's gonna be a scalar multiple of vector V. So you could see W sub 1, I already highlighted that, and here's vector V. Now, for both cases, they are scalar multiples, but the case on the right side, you could see that they're going in opposite directions. So that is because the scalar is negative, perhaps, and that's why the direction was switched to the opposite one. So we're going to call those two vectors, vector W sub 1 and W sub 2. They're going to be the vector components of our original vector U, which is the one that we're going to break into two vectors. So we are going to be given vector U and vector V, and then from there we will find W sub 1 and W sub 2. So how are we going to do that? Well, first we're going to find W sub 1. And then second, we will use W sub 1 to find W sub 2. So if we are saying that W sub 1 and W sub 2 add up to U, then if I solve for U, it will be on this equation, it will be U minus W sub 1, and that will give me W sub 2. So we're gonna find W sub 1 first by using the definition that we see here, and we will look into the steps. There's a formula, so we'll go over that in a minute. And then once we have found the first vector, the vector component, then we will subtract or find the difference of vector U minus the one that we found, and that's how we will find the second vector. And so that guarantees us that W sub 1 and W sub 2 will be orthogonal. Okay, so what we see here of W sub 1 is a projection of vector U onto V, and it's denoted like this. And so you could see that it will be on the drawing on the left, it's almost like if W sub 1 was an extension of vector V, and like we said, is a scalar multiple, so that if you were to draw a perpendicular line, as you could see here, if you were to draw that perpendicular line, then you will have a 90-degree angle between well, I feel like I just repeated myself. The line is perpendicular from vector W sub 1, but if you were to just connect, that's what I should have said, the terminal points of both vectors, W sub 1, which is the projection of U onto V, vector V. So the reason, what you want to obtain is that if you connect those two terminal points, then it will be a perpendicular line, and therefore it will have the 90-degree angle in for the intersection. Similarly, if we look at the one on the right, we are saying that W sub 1 is the projection of U of this one onto V, and in fact we said it was a scalar multiple, so that if you connect the two terminal points of vector W sub 1 and U, if you were to connect those two, you will have a perpendicular line to vector W sub 1. And if it is perpendicular, you know there is a 90-degree angle. So now let's go over step number 1, the steps and the formula. So from the definition of vector components, you can see that it is easy to find the component W sub 2 once you have found the projection of U onto V, which is vector W sub 1. To find the projection, you can use the dot product as follows. So we're going to go over all the steps that we have here are going to be how we're going to derive everything to find W sub 1, which it is the projection. I need to see how it is written, of vector U onto vector V. That is what we have here. So again, we are trying to find two vector components that will be orthogonal, and they are the addition of those two, that's why we call them components, will give us vector U. So at the end of deriving this formula, or doing the steps that I'm about to show you, we will end up with the formula required for to find the projection, to find W sub 1, the first one of the components. So first of all, we already know that vector W sub 1, it is a scalar multiple of vector V. And we call it scalar multiple because this one here is just a constant or a scalar. It could be longer than V if C is bigger than 1. It could be shorter than V if C is smaller than 1, or it could also face the opposite direction of V if the constant was to be negative. So remember, this 2 W sub 1 is nothing but a scalar multiple of vector V. So from here, what we're going to do next is take the dot product of each side with vector V. And that's what the step that you could see here. So we do that to both sides of the equation, and the parentheses that you see here are like if we just put them around our previous step, the right side of the equation. So after doing that, based on the rules that we went over with the dot product, what we have to do is distribute the dot product to each term inside the parentheses. And that's why you see here, I'm going to highlight it with blue. So dot product, we also have it on the left side. Remember, we took the dot product on each side. Then let's go to the next step. So from here, the dot product of a vector with itself, that was one of the rules that we had, it's equal to the magnitude of that vector, but square. And we did that before on one of the previous slides. So because of that, we're going to substitute this part right here with the magnitude square. That's what you see there. and then constant C is still there. Okay, now remember how we said that W sub 2 was gonna be orthogonal to W sub 1. So here we're gonna say that W sub 2 and vector V are gonna be orthogonal as well. So remember, if they are orthogonal, it means that the dot product of those two is equal to 0, and that is because the angle in between them is a 90-degree angle. So let's see if we can see that from here. Yeah, and I know I have a lot of stuff written down, but if you look at vector W sub 2 is here in blue, and then vector V is here, so you could see perfectly that there is a 90-degree angle there. So that's why those two are orthogonal. So we could calculate this operation, and it will be 0. So then we're just left with this side of the equation, well, this form of the equation, which will be the dot product on the left, and then on the right side we just have C and times the magnitude square of vector V. So if I just reverse them, it will probably make a little more sense if I do that. So if I write C times the magnitude of vector V square is equal to the dot product of U dotted with V. And from here, what we're going to do is solve for the constant C. And you can, on the next step, you can see what's going to happen. So the magnitude of V square is actually multiplying to the constant C, or the constant C is multiplying to the magnitude square. And so it makes sense that if we take that across the equal sign, it's going to be dividing. So that's what you can see here on the right side. And so it's going to be dividing the dot product of U dotted with V. So now from here, we're going to replace the constant with this whole expression. And that is what you could see here. C. And for that, you could also see it right here. So that is what we are replacing. And for the other vector, for vector V, that will be here and here. So we will be finding the constant, and then after that, we will multiply that constant by vector V to find the projection of vector U onto V, which will represent W sub 1. And that is the first step into finding the two vector components, W sub 1 and W sub 2. So remember that also we said from the beginning, from the diagram, that vector W sub 1 is a scalar multiple of vector V. And it could look like, if this is vector V, it could be like an extension of it, or it could also turn out to be, if the scalar was negative, it could be going in the opposite direction. Like this will be W sub 1, W sub 1, and then here this is vector V. So what we're doing, or what we did, is derive the way that we will find that constant right here, so that we could turn that vector U, that vector V into our projection onto U, so that it will be orthogonal with the second component, which will be W sub 2. And remember to find, this is a hard part, to find once you have found the scalar. Here's the scalar. And remember vector v, that was a given. So of course, when you multiply that, a scalar times a vector is actually going to give you a vector. So let's call it a v, not v, but so it will be, we're going to call it w sub 1. So it will be like w sub 1, let's say sub 1, 1. And then W sub 1, 2, just to indicate like horizontal and vertical components. But yes, it will have two numbers there because you're multiplying a vector times a scalar. All this formula is just to find the scalar that will guarantee that W sub 1 will be orthogonal with W sub 2. So let's see how this works. We have here two vectors, vector u, which is here, and we have another vector, we call it v, and that one is here. So if you look at the angle in between them, you could see that it is not 90-degree angle. It's not a 90-degree angle, and so that tells me that the vectors are not orthogonal, and we want them to be orthogonal. So what do we need to do? Well, we need to find two vectors, and actually this is wrong, very, very wrong. I'm going to highlight them again. Oh no, that was correct. That was correct. I was thinking that vector v was just this little part, but no, that's w sub 1. So in fact, it is the long one. That is vector v. So yes, we were okay. And here the angle, it looks like less than 90, so it is an acute angle, so obviously they're not orthogonal. If you're not sure, what you could do is calculate the dot product of u times v, not times, but u dotted with v, so it will be 6 times 3 plus 2 times negative 5. And remember, we get one number only, a scalar. So this is 18 minus 10, which will equal to 8. So that is the dot product. So that tells me definitely for sure that u and v are not orthogonal. So then we have to do the hard work. So we have to find the projection of u onto v. And in other words, w sub 1. That's like our first step. First step, find w sub 1. So from the previous couple of slides, we already have the formula, and we know that this thing is the scalar. This is going to be a number. And then here for vector v, we will be using the coordinates of the terminal point that we have here. So let's start substituting or finding things. So first of all, we already found the dot product. It's here of u dotted with v. So that is equal to 8. And now let's go ahead and find the magnitude of v. And so that will be the square root of 6 squared, the horizontal component squared, plus the vertical component squared. So from here, we're going to get the square root of 36 plus 4, which is the square root of 40. And I mean, from here, yeah, let's go ahead and simplify it a little bit. So the square root of 40 is the same as the square root of 4 times 10. So this is the same as the square root of 4 times the square root of 10. And the square root of 4 is 2. So we're going to have 2 times the square root of 10. Let's just leave it like that. But now, oh, actually, I didn't have to do all this. I'm sorry. We could just leave it as the square root of 40. And that's just because I forgot that for our formula, we need the magnitude squares. So if the magnitude of V is the square root of 40, but we need the magnitude square, so we square here and here, then the idea is that it will just, the square root will cancel, and so the answer will just be 40. There we go. So we put a 40 under here, substituting that with the square magnitude right there. So that is highlighted in blue, and then let's do the dot product with a different color. Actually, let's just highlight it pink. So it's right here, the dot product. Okay, now we are still, and I'm actually going to need more room here. We had an 8 and then a 40, and then we're still going to multiply by vector v. And instead of parentheses, I'm going to use the correct notation that this book is using. And so that will come from here, 6 and 2. Now we could reduce or simplify the scalar here. So both numbers are divisible by 8. So 8 divided by 8 is a 1. And 40 divided by 8 is a 5. So we're going to be distributing 1/5 to the vector. So the scalar that we worked so hard for, it's 1/5. So if we multiply that, we will get the result that you see here, 6/5 and 2/5. And that is because if you multiply 1/5 times 6/1, it will be 6/5. So that's how we get that. And so this here are the coordinates of W sub 1. Now that vector is going to be here. And so it just happens because the scalar is 1/5, is smaller than 1. W sub 1 is actually shorter in length than vector v. So it doesn't have to necessarily be an extension as in longer, but it could also be like a reduction of that vector in terms of length. So now that we know one of the components, which is W sub 1, we could find the second component, which is W sub 2. And we already discussed how to find that, but so you remember, the whole purpose of this is to decompose U so that it is W sub 1 plus W sub 2. So if we solve for W sub 2, it will be U minus W sub 1. And if we just reverse the order, it will be W sub 2 is equal to U minus W sub 1. Not the order, but the position of the, switch the left and right side. Okay, so the formula is here. So for W sub 2, we're going to get vector U, which we have here, the original, 3, -5. And then we're going to find W sub 1, which is what we found from the previous step right here. So that will be 6/5, 2/5. And so you already know that we're going to subtract horizontal components, and then we'll do the same with the vertical components. So this is going to give us W sub 2 is going to equal to 3 minus 6/5, and then -5 minus 2/5. Now here we have whole numbers and fractions. The whole numbers have a denominator of 1, and so we have to convert them into fifths. So W sub 2 will equal to 3 in terms of fifths is 15 over 5. And remember, we're subtracting the 6 over 5. Then we need a comma here. And we have negative 5 into fifths. It will be negative 25 over 5. Minus 2 over 5. Okay, and remember that this by itself is the horizontal component. And then here, this one will give us the vertical component. And we're still just finding W2 or W sub 2. So from the horizontal component, 15 minus 6, that is equal to 9. So 9 over 5, comma. For the vertical component, we will have negative 25 minus 2 is negative 27. And the denominator is a 5. So now what we could say is that W sub 1 is what we had here. Where is it? Oh, yeah. Actually, 6 over 5 and 2 over 5. That's what it is. And then W sub 2 is the one here. So if we want to check if we add those two, like it says here, and let's see if we get what we had originally for vector u. So that will be u is equal to W sub 1, which is 6/5, comma 2/5, plus W sub 2, which is 9/5, comma negative 27/5. So if we take, remember we got to take the horizontal component, so that will be 15 over 5, comma, we add the vertical component, so 2 minus 27 is negative 25/5. And of course, if we divide, 15 over 5 is positive 3, negative 25 over 5 is negative 5. So that is vector u. So yes, it is true. And what can we say about W sub 1 and W sub 2? There should be 2. That they are orthogonal. And also they form, if you add them, and they are the two vector components of vector u.